Here, just I want to give you some examples about the calculation of electric field in the case of a symmetric objects. Let's take first of all an example. Let's say we have okay, here we have this. We can say it's like this. We have this line charged positively with a charge density lambda. Okay, we have lambda, and here we have the x-axis. We can write the x-axis like this. Okay, and we want to calculate the electric field at the center O. Okay, in general, the equation of the electric field dE, we can say dE equal dEx plus dEy. You know, this object is symmetric because if you cut like this, you see that the object is symmetric about this vertical road. Here you have the same symmetric on the other side. It's symmetric. So we can cancel EX or EY component. Let's say how you can solve it. We had one example like this. What we have to do, you take a small portion on this side and the other one on this side. Okay, let's say here it's black and here it's red. The red one will create at the point O here, you know, a field like this. So the field at the point O must be like this. Okay. This field has two components, EY and EX. This is for the left one. So here we have EY and EX. And here we have E. We can say to the left, to the right portion, to the right, this one. Okay, here we have EX right, EY right. And to the left one, here, will create a field. This charge is positive. So the created field must be like this. And this one has X component and Y component. So here we have we have E left, EL, and here we have EL X component, and we have EL Y component. EX, this quantity of charge is equal to this quantity of charge and the same orientation. So this ELX and ERX have the same quantity as magnitude, but they are in the opposite direction. So the total, we can say here, E x r equal minus E x l. But as magnitude, EXR equal EXL. So we can cancel these two values. Finally, we can cancel the x component, we get only the y component. And you solve this like this. We have DEY as magnitude, and you know the y component in the negative direction. And you continue the solution. Now, let's take another example. And we find the symmetric and which component we must cancel. We can say, for example, we have the same shape, but we can say it's like this. Okay, here we have a line with we can say with lambda electric charge and with q charge. Let's say here we have just the y-axis. You see here you have y-axis. It's just y-axis. It's not a line. We have the blue line, okay, charged object. And we want to calculate the electric field at the point O. As you see now, this object is symmetric. Because it's symmetric, this object is symmetric. How you know? Because if you do a line like this, we have here this part is opposite to this part with respect to the x-axis. So this part and this part are symmetric with respect to the x-axis. Here we have a symmetry. So what we have to do now, I want to know the value of DEX. We have DE equal DEX plus DEY. I want to know which one we can cancel, the x component or the y component. What we do, we take a small part from this side, dq, and also another part from this side. It's positive, okay? If we take the electric field created by this one, by the black one, it must be like this because it's positive. And if you draw a line like this, it must be out, away, because it's a positive charge. So this field has two components, EX and EY. EX and EY. Here we have E like this. We can say E black. Here we have EY black. And here we have EX black. You know, this is y-axis and this is x-axis. And for the red, we can do the same. As you see here, we have a positive charge, so E must be in this direction. like this. So here also we have two components. We have E, Y for the like this, and here we have EX. So this one, the red is E red electric field. It has two components, E red Y component and E red X component. As you see, the quantity of this charge is equal to the quantity of this charge, and the angle theta equal to the angle theta. So you see here the y components EYB and EARY are equals as magnitude, but they have an opposite direction. So the total must be cancelled. In this way, we have to cancel the y component and we keep the x component. And you can write dE equal dEx as magnitude, and dEx is in the positive direction, plus I. Okay? And we can calculate the value. In the two last examples, we take Q as a positive direction. If you have Q is negative, you get the same result. Okay? You have the same result. Let's take another example. Here, in this example, we have this road which has a charge density lambda and positively charged equal to Q. Now, as you know, this road has a length L. If the x-axis passes of the y-axis pass in the center of this object, in the center. In this case, the road, we have a symmetric situation in this case. You have the right one and the left one. They are symmetric about the y-axis. The same shape to the right and to the left. In this case, in general, if you write dE equal dEx plus dEy, I want to know which component can we cancel, the x component or the y component. What we do exactly, as we said, we take two small portion to the right and to the left, like this. Here we can take the yellow color. Here you have dq, and on the other side we can take dq. Okay, for the black one, I want to calculate the electric field at this point, at the point P, at the point P. So the black one will create at the point P a field like this. This field EB, E black, has two components, EX and EY. Okay, we write the notation. E black has E black X component and E black Y component. And the yellow E1 will create also a field in this direction. Also, it has EX component and EY component. So here we have E yellow. You can E yellow. Okay, you can say E. I don't want to write yellow and Y in the same. And here you have E. Here you have E Y. Excuse me, EX. And here we have EY. As you see here, we can cancel the X components because they have the same magnitude, but they are in the opposite direction. In this case, we cancel the X component and we keep the Y component, and we do the calculation equal DEY. In this case, as you see, EY is in the positive direction. You can say equal D, EY in the positive J direction, and we do the calculation. Let's take another example for the same road, but the road it's in this direction. Okay, we repeat the same calculation. This road, excuse me, let's say the same example, but in the case we don't have a symmetric. What I mean, we have the same road here, and okay, here we have the same road, and the X pass at this side. Okay, here we have X axis and Y axis, Y and X. Okay, you know that I want to calculate the field at the point P. Is this object is symmetric in this case? Let's see. If we take two portions at any position, let's say here and here, we can say here we have a red, and we calculate the components here, and we will see if we have two opposite elements or not. The red one will create at this point a positive charge, a positive field like this, with two components, EX and EY. Here we have we say E1 with E1X and E1Y. And the yellow one will create with the same manner here, will create like this. We have E2 with two components, E2Y and E2X. Here we have E2, E2Y, and E2X. You see here, we don't have two opposite components. ex1 and excuse me here. Here it's ex and here it's ey. Okay, here we have e1x and here we have e2x, e1x, e2y, e2y, and e1y. Okay, you see here e1x and e2x have the same direction, so we have to add e1x and e2x. And here we have e1y and e2y have the same direction. So the final, okay, we are talking about DE, not E, DE. Okay, it's the same, the same. So the total DE equal DEX plus DEY. So you have to keep the value of the X component and Y component, and you do the calculation for these two components. Okay, so in this case, the object is not symmetric about this axis. Where we have the point here. These two components must be taken into account. I think now you have to understand the idea when we have a symmetric where we don't have a symmetric. For any object, I have to resume now. For any object, if you want to know the object is symmetric or not, you take two portions to the right and to the left, or near the extremities of the object, and you draw the X component and Y components of the field created by these two small elements. And you see if you have a opposite components or not. Okay, thank you.